This project is about temperature control using fractional PID in a distributed control system. We will demonstrate first the system in a distributed control. So here we have the PC or laptop as the publisher, and this other PC here is our subscriber. Okay, this is supposed to be the remote PC, and this one is the local PC. So right now, the remote PC is reading data from the local PC, which is supposed to be the server. So, as the temperature transmitter here changes, right now it's reading 50.11. On the remote PC, it is also reading 50.18 something on the meter. So the meter reads the actual data from the remote PC. So this is actually a demonstration of remote monitoring. Now, we will demonstrate remote control. Okay? The remote control will be executed by the remote PC. So here we will change the set point. So from this remote PC, the set point is set to 55. And as you can see here, in the local PC, there is a reading also of 55 on the remote set point. So this is a demonstration of a control part of the DCS. So both local and remote PC displays the same screen. Okay, all parameters are plotted on the screen. We will now demonstrate the operation of the PID controller in different modes. The first mode is proportional. As you can see, we switch off the fractional order, and the integral and derivative are both set to 0. Now, the control variable is changing. The set point is set at 50%, which is indicated by the red line. But the control variable never reaches the set point. There will always be an error. We change the setting of the proportional gain KC into 10, increasing the proportional gain. Notice that the control variable is almost reaching the set point. However, there is still an error, but the offset is now less than the previous. The proportional gain is changed to 20%, and look what happened to the control variable. It is oscillating. This is an indication that the system becomes an on-off control. It is now cycling. We now added integral control to the system, and notice that the cycling is gone. And let us see what happens to the error if we add an integral of 0.08. Upon adding 0.08, the integral control is actually eliminating the error. As you will notice, the control variable is reaching the set point. At this point, the fractional order is still switched off. We're still running the proportional plus integral control, but this time we're going to introduce a load change. Please click the valve to operate. Okay, with the load change means we're going to close the valve. Now look at the control variable. It goes down, and then, however, because of the integral control, it's correcting itself again. Okay. At this point, we have both P, I, and D operating with fractional order alpha. Notice that the fractional order output is now plotted also on the screen together with the integer PID output. However, the fractional order output is still exhibiting some overshoots, and it did not settle at the set point. Okay, we have reduced the fractional order alpha to 0.2, and notice the improvement in the response of the system. The fractional order controller output is somewhat similar now to the PID, the integer PID controller output, and they're almost reaching the set point at the same time. However, there's still some overshoot on the fractional order. Okay, we have changed the value of alpha to 0.02, which is the best value found so far, and the performance of the fractional order controller is now almost the same as the integer PID controller output. Notice that the control, both fractional order and PID control, integer PID control are both reaching the set point and stabilized at the set point of 50%. And they're both coinciding with each other. At this point, we will now demonstrate or show the output of the PID controller, fractional PID controller, through voltmeters. So a set point of 50% here will translate into 2.5 volt. The data acquisition box from National Instrument can only output up to 5 volt. So let's switch on the system. As you can see, the control variable is increasing, and it is shown on the right voltmeter an output of 38% is shown as 2.23 volts, whereas the set point of 50% is also shown here as 2.487 volts. So the process variable is now stabilizing at 50%. And the voltmeter on the right side shows the control variable in the form of output voltage to be 2.49 volts. That is exactly the same as the set point of 2.487.